Okay, again, this is most important thing. This is, or at least it should be, compatible with today's physics completely. Okay, now let us move to future physics. Lucky us. So this is speculation that is mainly based on these things and some other, of course, but let us see. Future physics. If we begin to observe an nature through physics with adjustment noted in the previous subtitle, it will lead us to some new and interesting domains, some of which are unthinkable in the current state of affairs. Some of the consequences are straightforward and easy to notice, some are hardly noticeable, but one only possible with help from stated assumptions. An other group of hypotheses only has some philosophically speculative links to this point of view. So, this is speculation from here downwards, but I think there is something that requests further investigation. Okay, let us see. First, yellow photon which starts its voyage at Earth's surface is more red near the surface of the moon. So if we climb up, it will be redder, and is more blue when it arrives at the surface of the sun. It has constant energy the entire trip, regardless of the change in color. So this is equation for that is equal h times n. So this frequency changes from Earth to Moon, from Moon to Sun, or other way around. It changes all the time, but energy of the photon is constant throughout all voyage. Okay. The masses of quark, electron, proton, neutron, specific atom, molecule, and every object depends on gravitational field. If we lift the object, we increase their masses, and if we lower them down, we decrease their masses. So this is the second thing that is hard to us to comprehend, because we are accustomed to some things, like mass of the electron. We said mass of the electron is 9.1, I think, times 10 to the minus 31 kilograms. Let me check. Just a second. 3 shift something 3. Shift 7 or 1. No. Shift 7 or 3. So mass of the electron, we say this is the mass of the electron. Let us see mass of the proton, shift 7 or 1. Mass of the proton, we said mass of the proton to be 1.77 times 10 to the minus 27 kilograms. And that is something that is imprinted in our consciousness and in our subconsciousness. And that is correct. But if you elevate this thing, if you take it from here and lift it up to here, you will increase its mass. Now, this mass is only for some situations. Here is greater, here is greater, and here is greater. Why? Because I invest the energy in elevation of it. And that is what is difficult to absorb to a physicist, because this is the hardwiredness. Okay, doesn't matter. Let's go on. With the change of mass, it's logical to assume change in size. Okay, of course. When you change in mass, you change in size. When you have larger mass, you're usually bigger. Length, height, width of the named objects. In other words, cat, electron, quark, atom are smaller under the table than they are on the table, and they are even bigger if you raise them to the ceiling. So if I take this thing, I not only increase its mass, but I increase its size. So it starts to grow. It is not notable here at the surface of the Earth, but in reality that is what's happening. For since the speed of light c is constant everywhere, it is interesting to note that increase of photon frequency in a free fall cause its wavelength to decrease. So the photon becomes smaller and smaller. So this thing, when it's free fall, I'm not going to tell you what's happening with it, but in the free fall, it remains energy, and if I catch it here, it is smaller here than it's here. And photon, when it's falling down, its frequency is growing up, but its wavelength decreases. Why? Because speed of light is constant. So, speed of light is equal wavelength and frequency, and because this thing increases, this thing decrease. Why? Because C is constant. So when frequency increase, wavelength decrease. So you become smaller and smaller. Even photon, not only objects. So now that is the first parallel between photon and objects. I go on. Gravitational force and acceleration equation. And now we come to some thing that I have to place in. Gravitational force and acceleration, this is my personal work, and this is the law which I'm stating. One of the major concepts, but this is actually consequences of this. I did derive this, but let us say for the sake of simplicity that this is the law which I'm stating. And this is the law that I'm stating. Just one second. The major consequence mass reduction in gravitational field are new equations for gravitational force and acceleration. There is a calculation for that, but I did not want to include this in the book because it will be too much a burden for it. The original equation is derived from the free fall of the small objects toward much bigger one. This is the generalized equation. It's necessity. It is introduced to accommodate Newton's third law and other things. Doesn't matter. All in all, this is the new force. This is new expression for the gravitational force. I have to introduce this. Why? There is several reasons for that. This is actually what I, like I said, for the motion of the small object around larger one, I did derive something very similar, but this is the generalization for that situation, and this is the gravitational acceleration. This is the gravitational force. So as you can see, this part here is Newtonian gravitational force, and this is what I had to add in order to accommodate observation. To be more precise, I first did not observation, but motion of the small objects in the presence of the large one, if the smaller one loses its rest mass. But it's actually I think what is really happening. This could be some form of Mond theory or that. So in any case, we will come back to this and see what is the consequence of this situation here. So this is the gravitational force between these two masses, let's say, on this distance. So if you have two masses, M1 and M2, they are steady here, and standard gravitational force will be this, and this is what I have to add. This is the, I think, improvement of the current situation. So, acceleration of the objects M1 toward the object M2, actually toward the center of the mass of the two objects, is like this. And now we have first interesting thing about this thing. First interesting thing about this is already said that function f and force and acceleration are defined for this. As you can see, if this thing here is smaller than r, in this region gravitational force is attractive with large values as r goes near to this. When r goes near to this, gravitational force, as you will see in the future, is most strongest force in the existence. So only by using this equation here, we could actually calculate what we are observing in nature and what we are observing in the nature. I'm not completely happy with the description of the black holes today, but with one thing I can agree in complete, that whatever object come near to your so-called event horizon, that object will break. If you take atom, if you take nucleus and placed near event horizon, it will break. So gravitational force in that instance is stronger than nuclear force within nucleus. Do you understand that? Gravitational force is stronger than nuclear force. If you look at Hawking radiation, it's even split the virtual particles on top. What is the force necessary for that? So, but let's not go there now. let us consider, if you take nucleus in one your hand and place it near event horizon, that gravitational force will split that nucleus in half. That is most definite thing. Why? Because nuclear force is weaker than gravitational force in that regions. And you need to have equation to describe that situation. And this is an attempt for that. We will see where will this equation lead us in the future, but for now that is this. And this is the extremely strong force in these regions that is actually strongest that force that is known to us. But there is other interesting situation. In a region when R is larger than 0 but smaller than this, in this region gravitational force is repulsive. So this here become repulsive force for some situations. We will see some examples where is that happening in our universe. That is what you call dark energy. That is also a very interesting situation. Okay. And you can see what is the realistic limit for density. Because of that, if you try to squeeze it more within this region, you will have that is gravitational fields force is repulsive. In some region that repulsive force is stronger than anything else, so it will explode violently if its object is relatively small, or it will explode not so violently if object is very large. So we will see about that in the examples. That is very interesting. But more or less there is a relativistic limit in, let's say, energy density for time being. Okay. Okay, that is not very important. So regions, and because of that, okay, that's not very bad. How much mass and energy can you squeeze into a sphere with radius of 1 meter before gravitational force become repulsive? That is the question. So near R, when R is near this here, it will become from very attractive to very repulsive force. So you see this is the limit when that switch is happening. And in that situation, gravitation, when you have 1 meter of this space, you could place 6.75 times 10 to the 27, 6 kilograms. This is what you can place in the region enclosed by 1 meter. And if you try to place more mass in this, then gravitational force become repulsive, and very much so. So it will be attractive, nothing more stronger than it. But if you want to place one marble above this, it will explode violently. So let us see what is the volume of that region. That is this, and this is the density of that region. If you dealing with 1 meter, this is the density of that region, 1.61 times 10 to the 27 kilograms per meter cube. So energy density associated with that is 1.5 times 10 to the 43 joule per meter cube. This is approximately the amount of energy you can put in a region encircled by 1 meter. Any additional energy and gravitational force become repulsive. Okay, now, second question that is also interesting. How much mass and energy you can squeeze into a sphere of radius 10 to the 10th meter before gravitational force become repulsive? And when you do that calculation, you could actually place this much mass. And that's in the radius 10 to 21 meter. Then you could place this much, and this is the density of that region, and this is the energy density. If you have a very large object, this is energy density where gravitational force become repulsive. More in next video. Stay tuned.